Today we're going to take a quick look at parametric equations. This should be a bit of a review from what you've seen in the past, but I'm sure we can all use the refresher. So there are times when we have motion that's not a function, that doesn't pass the vertical line test. So something like this is not a function, but we may still want to describe that path, and it's often more easily done through parametric equations. When we describe x and y each as their own function of another variable, we usually use t or theta. So we would write this as x equals a function of t and y equals a function of t. And these are what we refer to as parametric equations. And we'll often restrict the parameter to be between two numbers, call them a and b. This doesn't have to be the case, but it's often the case. So let's take a look at these parametric equations right here. X equals root t, y equals t, for values of t greater than or equal to 0. We'll take a look at how we can deal with these on the calculator. So we can graph these by going to your graph entry and changing it to parametric mode. And we can type in the equation for x, the equation for y, and we can specify the values of t. And this is just a thing with your calculator that it requires you to specify values of t. So even if the function we're looking at is from negative infinity to positive infinity, the calculator needs you to specify some bounds on t, otherwise it just can't handle it. So if we have values of t greater than or equal to 0, let's just graph values of t between 0 and 10. We could make that upper limit larger if we needed to, but we'll see if 10 is enough. And the t step, that tells the calculator how accurate to make the curve. If you make that value smaller, like 0.01 or 0.001, you'll get a smoother curve, but it's going to make it more difficult on the calculator to create the graph. So a lot of this stuff here is just kind of us telling the calculator what to do. All right, and here we go. There's our parametric curve. And we can change the viewing window. And we can confirm that this is what our graph should look like algebraically using substitution. Since y equals t, replace t with y, and we get x equals root y, or x squared equals y for values of x greater than or equal to 0. And that's exactly what you would expect this thing to look like. So we took this curve in parametric equations, and we were able to convert that into Cartesian equations to put it in a form that we're more used to seeing. Now, this can be done in this case. It's not something that can always be done. All right, let's take a look at a circle in parametric equations. We let x equal cosine and y equal sine for values of t between 0 and 2 pi. We know that sine squared plus cosine squared equals 1, which means x squared plus y squared equals 1. So if x equals cosine and y equals sine, this gives us our equation of the circle that we're used to seeing. X squared plus y squared equals 1. That's a circle of radius 1. So what we've done here is, again, what we call eliminating the parameter. We took the parametric equations, x equals cosine, y equals sine, and we got rid of the t. So we turned that into x squared plus y squared equals 1. That's a more familiar equation we're used to seeing. But again, this is not something that can always be done. It can only be done for certain sets of parametric equations. All right, let's graph this on the calculator. X equals cosine, y equals sine from 0 to 2 pi, which is 6.28. So there's our circle. Let's change the viewing window because that's pretty small. So we'll change our window settings. And notice it doesn't look like a circle now. So we can use zoom square, which makes everything, all the axes are now the same units. Okay, we can examine this curve by using the trace function. So menu, trace, and it puts this little cursor on here, and you can arrow left or right, and you can examine different points on this curve. So you can see right here, x is 1, y is 0, when t is 0. And we can change direction and find more points on that curve. All right, now your calculator can graph conic sections without having to use parametric equations. So if we clear our graph and follow these steps right here, go to equation, choose the equation for a circle, You'll see there that there's also equations for hyperbolas, ellipses, other conic sections, which are not functions, but they're still equations that we might want to graph. And you can graph it this way. And we can see that x squared plus y squared equals 1 squared gives us the exact same graph as cosine of t and y equals sine of t for values of t between 0 and 2 pi. All right. These are the parametric equations for an ellipse. So notice a circle, one of your variables would be sine, the other one's cosine. For an ellipse, if you have a coefficient there where the two coefficients are not equal, that's going to create that ellipse. That's going to make it so it's kind of stretched in one direction. And we can eliminate the parameter for this one by dividing by 3, dividing by 4 to get sine and cosine alone. And then we can use sine squared plus cosine squared equals 1 to allow us to come up with the equation in terms of just x and y. All right, so we've seen two techniques for converting from parametric to Cartesian. We can eliminate the parameter, which is where we solve one of the equations for t, and then we substitute that into the other equation. And that method's only possible when the graph is a function, when it passes the vertical line test. The other method we can use is the Pythagorean identity if the equations we're dealing with have sine and cosine. Now, if we don't have either of those two cases, then we just can't eliminate the parameter. There are many functions, or I shouldn't say functions, there are many equations, many graphs, that can only be described parametrically. Okay. Now, here's just to point out that going the other direction, if we have something written in Cartesian equations, we can go to parametric equations very, very easily. We replace x with t, and then you let x equal t. Here's what that looks like. We have this equation, replace our x's with t, and let x equal t. Now we have parametric equations, and that works every time. So going this direction is not nearly as challenging as going from parametric to Cartesian.